Hi everyone, I'm Chrafih. First of all, I would like to thank the organization committee for accepting my presentation work. I'm from Department of Physics, Faculty of Polarizability, Brimila, Morocco. My subject is directed by Professor Khalid Rahmani and Professor Azdin Zorqani. My subject entitled Temperature Effect on the Diamagnetic Susceptibility and Polarizability of a Shallow Magneto-donor in Quantum Box GaAs ensured by GaAs doped in aluminum. So during my presentation, I will follow this plan. So I will introduce by a small introduction, then we will see the classification of low-dimensional materials, and we will see the numerical modeling of quantum confinement in our samples. So after we will see together the effect of temperature on the low parameters of the quantum box. Then I will show you the different results and discussions, and I will conclude with the conclusion in the perspectives. We call the nanomaterials with non-scale grain size. So when the size or the dimension of a material is continuously reduced from a macroscopic size to a very small size. So when the properties remain the same at the first, then a small change began to occur. In this way, we formed a new structure of materials, so-called nanostructures or nanomaterials, and we are more interested in the thin films or nanolayers 2D. So the field of research and development in several fields of nanoparticles, we have the optoelectronics, the functioning of electronic devices, and in the medicine by the laser, and the surgery by lasers. The classification of low-dimensional materials by their degree of confinement, we found the three-dimensional materials or the bulk structure, or the electron and holes are free to move in all the three dimensions of the space. And we have also what we are interested in, so the two-dimensional materials, or that we call it the quantum wells, the thin films, or the electrons and easily moves in the two dimensions of the space. These structures are formed in semiconductor by having materials sandwiched between the layers of materials with a wider band gap. And we have also then the materials in one dimension, and the nanoparticle or zero dimension, or the electrons in confinement in the three dimension of the space. So our samples or our heterostructure is formed by GaAs material semiconductor surrounded by or sandwiched by the two of materials with wider band gap. So it's GaAs doped with aluminum. So the compound GaAs and RL GaAs belong to the group of Chrafih, or they crystallize in the zinc blende structure, consisting of two subrhizoid with decentered faces. So the compound of the compound GaAs has a direct band gap, or the minimal energy transition between the two bands can take place without changing the wave vector, so which allow the absorption and the emission of light much more efficiently than in the indirect band gap materials like GaAs. So as I said, so we are interested for the influence of the temperature and diamagnetic on the diamagnetic susceptibility and on the polarizability of shallow donor confined to move in a structure or in quantum box made of GaAs ensured with GaAlAs with uniform magnetic field. So the parabolic bands are more effectively for the emission and absorption of light is much more efficiently than in the indirect gap materials like GaAs. So the problem or the difficulty is the existence of impurities of the elaboration of the quantum box. So the impurities can be incorporated into the semiconductor, so where they are inserted in the growth of by the diffusion or in the elaborations. So the presence of the impurities so can be change the properties, the optical properties, the electronic properties. So the geometric content can be controlled by the size and the shape of the structure as well as by the choice of the material barrier. So in our case we are formed the structure or the samples by the equation of Schrodinger's, like we see. So we have to solve in the Schrödinger equation to monitor the electronic properties. The influence of the temperature on the systems or the shallow donor confined to move in the quantum box made of GaAs surrounded by GaAlAs with a uniform magnetic field. So we are using the Haas variational method within the effective mass approximation. It's used in the case of finite barrier confined potential. So the calculation we have taken account of the electronic effective mass, the electric constant, and the conduction band offset between the dots and the barrier varying with the temperature. So the conduction band offset parameter can be differentially by under the temperature between the dot and the barrier, as you see. So where there is an important of the concentration of the aluminum. For the GaAs quantum dot, the parabolic conduction effective mass is determined under the effect of the temperature. This is determined from these expressions. So we will see the effect of the temperature in the expression of the effective mass and on the dielectric constant. So to examine the electronic properties of the energies, or we have to solve the Schrödinger equation. So when the impurity is placed at the center of the dot, so the Schrödinger equation for the material can be solved exactly. So that we have choose exactly the trail wave function as you see. And we respect the dimension of the quantum box. So the Rn is the normalization factor and AB are variational method. And for determination the diamagnetic susceptibility, we are under the influence of the temperature. So the expression is like you see, where the air is the main square distance of the electrons from the nucleus. So we have attached the electrons to the impurity to know exactly where the distribution of the impurities under the structure and the move of the impurities and their efficiency in the properties, optical properties and electronic properties. So we can represent here the variation of the lattice parameter as a function of the temperature for different value of aluminum composition. So we notice that the lattice parameter increase with the temperature for all values of concentration. So the when the increasing of the temperature, the interatomic distance in the cubic lattice increase. This has the effect of increasing the lattice parameter and the lower the gap. So, to evaluate the temperature effect on the diamagnetic separator, we have to plot the diamagnetic and the effect of the hydrostatic pressure for the dimension of the quantum box. So, from the first figure, we can observe that the absolute value of the diamagnetic susceptibility increase with the width of the quantum dot for the different temperature value. And be noted that for a fixed temperature, the absolute value of the diamagnetic susceptibility increase as the quantum dot increase. This is related that the fact at a specific temperature the wave function is more compressed for a small quantum dot. So for the second, we are study the magnetic field effect on the diamagnetic susceptibility. So the variation present the diamagnetic susceptibility as a function of magnetic field for different value of the weight of the quantum dot. So our results show that in the absence of the temperature, the magnetic field effect is remarkable only for the large quantum dot. So when the magnetic field increase, the absolute value of the diamagnetic decrease, and for the small value of the quantum dot, the influence of the magnetic field is masked because the geometric confinement is more pronounced. Here we have plotted the polarizability as a function of uniform magnetic field. So we are see that the polarizability decreases by increasing the magnetic field. So this behavior we can mention an explanation according to the wave functions. So this is due to that the wave function which depend on the temperature is more localized. So we notice that the magnetic field reduces the polarizability. So this finally depends strongly on the effect of the temperature comparison with the presence of uniform magnetic field. So on the other hand, we show the variation of the polarizability as function of the width of the box for the two cases, in the absence and in the presence of the magnetic field. So that we have seen that the polarizability increase by increasing the width of the box. So we are seeing in this presentation the effect of the temperature and the magnetic field or uniform magnetic field on the diamagnetic susceptibility and on the polarizability of hydrogenic donor placed at the center of quantum box that are made of GaAs ensured by GaAs doped by aluminum. So it's observed that the effect of the temperature in zero-dimensional semiconductor is appreciable for the large quantum dot. So the temperature increase the absolute value of the diamagnetic susceptibility. On the other hand, the susceptibility decrease by increasing the magnetic field, and its effect is recorded for the large quantum box. So according to our results obtained, so we have found that the temperature and the magnetic field play important roles in the polarization in the quantum dots. So this result maybe is good results for a great influence on the fabrication of semiconductors in the presence of donor impurities in the quantum dots. And thank you for your attention.